Well, good afternoon, everyone. We're going to change things a little bit. I think there has been a lot of talk about language. We're going to go to the visual domain in this talk, and we're going to talk about pre-training of text-to-image models. But first, let's give us a little introduction about us. My name is Pablo Pernias. I come from Spain. I currently work as a research scientist at Luma AI, where we're doing a lot of super interesting work on generative models. Before that, I was working at Scalability, also on image models. And even before that, I was at Disney with Mikel, who already introduced me, and doing also a lot of cool work on media and analysis.
All right, my name's Dominic, and we both work at Luma currently. Before that, we already worked together at Scalability AI. That was the first time that we worked on a large-scale project together. And before that, I was also more on a generative AI side in the visual domain at a company called Wand that was doing like a nice interface for using text-to-image applications.
All right, so now let's talk about text-to-image. I don't know how many of you know about text-to-image. We're going to try to give an overview of the different techniques that have been used during the past few years. And the first one, maybe it sounds familiar to some of you, was DALL-E 1. It was released by OpenAI. I would say it's the first text-to-image model that was actually impressive, that generated things that caught the attention of everyone. And one thing that was very interesting about DALL-E is that since OpenAI, well, probably you know OpenAI is doing large language models, ChatGPT, the first text-to-image model that they did was trained to do basically the same thing as an LLM, right? So there's something that we can find in common between image and text. How did it work? It worked on next token prediction, just as LLMs, right? But how do you do this on images, right? So you have to start with an image. How do you turn an image into some sort of text sequence that you can then try to predict the next word? You have to split the image into chunks, right? We'll consider these chunks are like words then. So if we have a large enough vocabulary of words, we can represent a very large majority of the images. Maybe we're not with the best quality, but we can then have this dictionary encode it, just as it was mentioned before with transformers, with language, using a visual tokenizer. And then we end up with this matrix of what we call the visual words, right? So now that we have our visual words, we can just treat this as a language model, just exactly as in a language, in a large language model. We can then take our matrix of visual words, flatten it into a sequence. It doesn't matter really the order. The image doesn't matter if it's generated from top to bottom or from bottom to top. It just needs to be a sequence. And then we can just use the transformers to predict the next word. Start from the top of the image, in this case, top left corner of the image, and then we predict the bottom, the top center visual word. Then we use this as part of the input again, and then we keep predicting word and word and word, right? So then once we have this sequence of words, of visual words, we can then put them back into a 3x3 matrix and convert it back into an image, right? These were the results that were achieved by DALL-E 1. You can see that the quality is not extremely good, but at the time, this was extremely exciting. The first model that could actually generate anything that you asked. Before that, we had GANs, we had some style transfer models that could be very good inside of a very specific domain, but nothing like this, right? But then this technique had some very severe limitations. First is that since you have to do this visual tokenization, you have to turn this image into a sequence. You need to work in a very low resolution. Otherwise, this sequence of words could be extremely big. We know nowadays we have some language models that can work with 1 million tokens. Back in the day when DALL-E 1 was released, this was not an option. So working with very large images was not something that you could do. Also, as I mentioned, we can predict the next token in any order, but that's not natural for images, right? Images don't, like, you don't interpret images as a sequence when you look at them. Maybe there's some better ways, right? So this was sort of like not a natural way to work with images. Also, the generations was very slow. For language models, you don't need to reach the 1 million token window in order to get something, right? You can start getting answers after a few tokens. For image generation, you cannot get a full image until you have generated the full sequence. So then you need to generate every time you want to get a new image, you need to fill the whole context, right? And that's very expensive. So can we use a better technique? This is where diffusion models came into action. I don't know if you've heard about diffusion. It's the technique that replaced autoregressive models for image generation. And I'm going to give a quick overview of how diffusion works. So everyone can say now that after this talk that they know how this diffusion, like stable diffusion, maybe you've heard about it, how they work. The core idea is that you start from a distribution that you don't know, like a dataset of images. You don't know how to represent this distribution statistically, and you try to map it to a distribution that you do know, like a Gaussian noise. Look, right? It's very simple to get a new image by sampling from Gaussian noise. But it's not easy to get a new image like from a specific dataset. So we want to do this mapping in both ways, right? So we start by doing the mapping in one way. We start from our image, and then we're going to be adding tiny bits of noise. Every time we add a tiny bit of noise, we turn the original image distribution closer to the noise, the Gaussian noise distribution, right? Until a point where we're fully into the Gaussian domain. Now we need to do the opposite, right? We need to start from noise, start from a very easy distribution like Gaussian noise, and go back to the original image by removing a little bit of noise, right? Seems easy enough, right? But this part, like the first part was super easy, adding noise. We know how to add it. How do we remove it? That's the hard part. For this is where the diffusion model comes in. We have to train a neural network to predict what noise was added in this step, and then so we can remove it, right? In practice, what we do is that we take our, in order to train these models, we take our input image, we multiply it by some value, we take our noise, like a Gaussian noise, we multiply it by another value, and then we add them. So we have now our input noise image. We pass this through the diffusion model, and then we can predict either the original image, which would be X0 prediction, what we call X0 prediction, or we can predict what noise was added to the image, which is called epsilon prediction, or some sort of combination of both. Like there's one very popular target, which is called V prediction, which is multiplying the image and the noise by some factors, right? So this is the base of how diffusion works. But how was diffusion used by DALL-E 2, which was the next iteration of the OpenAI models that replaced these autoregressive models by diffusion? In their case, they did something quite clever, right? So they didn't have they didn't have a lot of compute to train this, or well, they did have a lot of compute, but they didn't have the knowledge to train this in a very large scale. So they took a model that they had pre-trained in the past. I don't know if you've heard about CLIP. CLIP is a model that's very interesting because it creates these embeddings like the ones that you use for RAG, but it can do it in a multimodal setup. So it can take images and text and embed both modalities into the same latent space. This means that an image and a text that's similar, like semantically, to this image will be close in this latent space. So we can find similarities between texts and images, or images and images, or text and text. So what they did for this text-to-image approach is start from to work in this very tiny latent space, the latent space of CLIP. So instead of trying to take text and turn it into an image, they tried to take text embeddings and turn them into image embeddings, right? This is a much easier task. Once they have these text embeddings that can be converted into image embeddings, they trained a model that could take image embeddings and convert them back into images, which they called unclip, which is the opposite of what clip was doing. Clip was taking an image, turning it into an embedding. Unclip was doing the opposite, right? So then they could combine these approaches. Then you have a text, you turn it into an embedding, you take the embedding of the text, you turn it into an image embedding, and finally you take this image embedding back into an image, right? There was a problem with this technique. Working at like this last step where you turn the embedding into an image is very expensive. So in order to be able to do that, they had to you had to work on a very low resolution. This means that the image that the model generated was 64 by 64. So what they did is that they added a couple of upsamplers. Those are models that can take a low resolution image and turn them into a high resolution image. And for this, they also used diffusion models. So these diffusion models were just like making the image bigger. And this is how they tried to avoid the complexities of working on high resolution with diffusion, which was very expensive. Here are some examples about for how the results of DALL-E 2 looked. The quality improvement is, I guess you can see it's huge, right? So DALL-E 2 came, everyone went crazy about diffusion. Diffusion became the new state-of-the-art technique to work with for image. But in terms of efficiently, we're going to say that this DALL-E 2 is the baseline, right? Since it works at pixel level. Pixel level is the least efficient you can get. Then I'm going to pass it to Dominic, who will explain how this advanced.
Yeah, so there was basically the proof of concept that we could use text to image or diffusion models to work or to do really good text to image models. Then there was a really interesting idea, which Pablo already mentioned and a lot of you already know, called stable diffusion, or the original work, latent diffusion models. And the idea or the observation that people did was that, hey, we do know some models that can compress images or can compress data to a smaller space. And what they did, they used a variational autoencoder to take the images, in that case, for example, 1024 by 1024, and compress it into 128 by 128, so an 8x spatial compression, while being able to reconstruct it basically perfectly. And that is now at this latent space, it's like working at just 128 by 128 pixels. So it's a lot more efficient, but you can decode it back into megapixels. So the way they did it is very similar to what Pablo already described, just with the difference that they, of course, encoded the images first into the latent space, as presented here as the encoder, and then everything happens in that latent space. But we know that everything translates because we know that images are basically kept intact in that small latent space, and you can decode it, so you can just train a diffusion model in that smaller latent space. And that makes a huge difference by being able to compress just 8x. So you take your image, you encode it, you have the latents, and then you do the normal setup that Pablo already said. You have your latent noising, where you add noise to your latents, and then you have your diffusion model, which tries to predict the denoised version. And a bit different from DALL-E as well is that you have the text conditioning being fed directly into this diffusion model instead of this being an upscaler. So you have all the generative and heavy lifting happening at this latent level, at this first and main diffusion model. And then the model tries to predict the output, and those could be any of what Pablo mentioned, X0, where you predict the denoised, you can predict the noise, or something in between. And that worked really well, and people really started getting at it, especially also because it was open source. The first series was Stable Diffusion 1.x, and 1.5 being the most used one, I would say. And it was very surprising, and not as good as DALL-E 2, but since it was open source, it attracted so many people and also started a hype of just working on those things and improving it. So that helped so many people understanding how diffusion works and how we can make that work better. They then scale it up with Stable Diffusion XL, which was a lot bigger, it worked at a higher resolution and had better prompt following and so on. So we classify this as sort of the next step for efficiency, where you take and start to compress stuff. So now that's where our work comes in. We thought about, could you go even further and compress stuff even further? Because you saw with the VAE, we do an 8x compression, and that's pretty nice because we can do we can encode this image into this 128 latent space. So the problem is, if you want to increase that even more, the reconstructions of a normal VAE become very blurry, and you lose a lot of high details in the reconstructions. But nonetheless, we knew that if we could increase that by a lot further, that would be huge, and we could have much, much more efficient training, and maybe even people with that have limited compute and don't work at these huge companies could train these models more efficiently. So we set the goal of trying to achieve a 42x compression, which means, in theory, that if that is possible, we can take the 1 megapixel image and encode it into just 24 by 24 latents, and also at the same time able to reconstruct it basically perfectly. So that was the goal, and to do that, we introduced the following pipeline. And by the way, the name of the work, which initially was not meant to go anywhere, but that's why we called it Verstian. And yeah, but it worked quite well at the end. So the difference, or actually it's very similar to a normal latent diffusion setup. And you have a latent generator, as in Stable Diffusion, the main model that works in the latent space, and you have something that decodes it back to pixel space. The difference here is that we have the latent decoder, which now consists of 2 stages instead of just a single one. But if you look at the latent generator, which we call stage C, it's very easy. It's very similar to Stable Diffusion, the only difference being that the latent space is much more compressed now. And as I said, if we just take those very compressed latents and are trying to decode them back into pixel space, we get very blurry reconstructions. So we introduced something that we called stage B. And if you're familiar with normal autoencoders, it is what we call a diffusion autoencoder. So you also use a diffusion model, which is a lot more powerful and has this iterative process, and which takes then these very compressed latents and then takes a few iterations to decode it back into a latent space of stage A. In theory, you could also already have that decode back to pixel space. The reason why we have this intermediate step, which decodes only back into a lower compressed space, is for the simple reason that even this training becomes more efficient if we use something like a VAE that works on an 8x compression. So we try to do a diffusion autoencoder that takes very compressed latents and is able to reconstruct them. As a rewind, that is the basic Stable Diffusion architecture. And the only thing that we did, and remember this is only for being able to encode and decode stuff, is that we added something where we could also condition on an image. So we take the images and we apply some compression. We first downscale, then we have a neural network that compresses it, and then some more downsampling channel-wise. And then we feed that as well into the diffusion model. And that is a lot easier for the diffusion model to reconstruct, because if you only have a text conditioning and get the text a cat, that could be infinite possibilities. But if you have a good representation of image embeddings, that's a lot easier to reconstruct. So this model trains a lot faster and also needs way less sampling steps. So that was the idea. And after a lot of experimentation and a lot of training, we ended up with image reconstructions that looked like the following, where on top you see the original, and then at the bottom you see the reconstructions, which look at the first, if you just look at it, very, very similar. And remember, those are literally taking the entire image and only encoding it to 24 by 24, while being able to decode it back into without losing much of the details. So with that said, that was very promising, and we were able then to take this semantic compressor, as we called it, which encodes the images into this very compressed latent space, and train a diffusion model, just like the latent diffusion model, like Stable Diffusion, in that very compressed latent space. And that makes it much, much faster, because your sequence length or your dimensions is so much smaller than if you work higher, because it grows exponentially and it becomes slower and slower. So after a lot of work on this, and also then joining Stability, where we worked on it, where it was eventually called Stable Cascade, when we released it, those were some of the generations that we got out of it. And yeah, we would currently classify this as being like a very interesting approach, especially if you're limited by compute, as a good alternative to the normal latent diffusion models technically it's the latent diffusion, but it just uses this additional branch of encoding stuff even further. And even though it may seem that this adds more complexity or more inference time when you try to sample, it turns out because all those stages have the benefit of the generative model working at this very compressed latent space, so it can generate super fast, and then the decoder is super quick. It doesn't need a lot of iterations. It's very quick and outperforms even Stable Diffusion XL in terms of inference time, even though those are at a similar size. And I guess a lot of you have also seen other works where diffusion was heavily involved. Some work that we have been working on now at Luma is video models, but I think you've also seen Sora by OpenAI, which really put a high threshold on how good text-to-video models can be. A lot of things happening in so many other fields like biology and drug discovery, with AlphaFold 3 being released very recently. But then also in the audio field, I don't know if you've heard of Suno and 11 Labs that have really pushed the state-of-the-art of text to music. And yeah, with that being said, I guess that was a quick introduction to how we pre-train and how we, in general, train text-to-image diffusion models nowadays on a lot of different domains. And yeah, thank you for the attention, and we're up for some questions if you have any.